Here we're going to go through dipoles and forces and torques from electric fields. An electric dipole is two equal opposite charges that are separated by some distance apart. So that's what we mean by a dipole. Two charges that are equal and opposite to each other. The figure shows an electric dipole and the electric field lines created by it. Draw a positive and a negative in the correct charge. Field lines run away from positive charges and they terminate on negative charges. How do the magnitudes of these two charges compare? Explain in two different ways. Well, they're equal. And one way we know that is that's the definition of a dipole. The other way we know that is that the number of field lines that are originating on this positive here on the bottom is the same as the number that are terminating on this negative charge. Two ways that we know those charges are equal. Now, say we have a test charge, which by definition is positive. Let's draw in the resultant force vectors that would act on the test charge at points A, B, and C. If we moved our little positive test charge around to points A, B, and C, what would we get here? This positive test charge at point A, it would feel a repulsive force from that positive charge, but it would feel a smaller attractive force towards the negative charge. And if we tip to tail those, we get a net vector that looks like that one right there. And you can see that that is tangent to the electric field line there. Let's see if that's the case for these other two locations as well. Let me draw the two partial force vectors with a pencil. So this positive test charge would feel a repulsion from this positive charge on the bottom. That's kind of hard to see. And it would feel an attraction, and that attraction would be stronger, wouldn't it? Because it's closer to the negative charge. So if we tip to tail these, hopefully you learned how to do that in another physics class, the resultant vector is going to look like that. And sure enough, look at that. It is exactly tangent to that electric field line. And one more time, if we draw the components, at point C, we're going to have a repulsion directly away from that positive charge, and we're going to have an attraction that's going to be weaker towards that negative charge. If we tip to tail those, you can see the case holds true again. The net force that any positive test charge would feel follows the tangent of the electric field lines. The magnitude of the force that any charge would feel if it's in somebody else's electric field is given by this equation right here. And if you do any work in electricity, you'll get a lot of mileage out of that equation. Now, the direction of this force, this is the magnitude of the force. The direction of this electric force depends on two things. One depends on the sign of the charge, whether the charge that's in the field is positive or negative, and what the direction of the field is at that location. The magnitude is given by the equation there. The direction is definitely going to be tangent to an electric field line, but which tangential direction, you might say, depends on what sign the charge has and what direction the electric field has. Now, suppose the dipole that we've been working with is subjected to an external electric field, that is one generated by some source that we can't see. Suppose also that the field is uniform and that its field lines are oriented as shown here. What are the correct choices? So now we're going to take our dipole that we have been working with, and we're going to put it in this uniform electric field, this uniform external electric field, which perhaps I'll just label it as E. We remember that the positive charge was on the bottom and the negative charge was on top. What would the net force be on this dipole? 0. There's going to be a 0 net force. And the reason for that is, you remember the equation we just wrote down. The force on any charge is equal to the magnitude of the charge multiplied by the electric field strength. The electric field is the same, has the same strength for this positive portion of the dipole as for the negative portion, and the charge magnitudes are equal, positive and negative. Therefore, there are equal and opposite forces on the two parts of the dipole. That's why the net force is zero. What about a net torque? Is there a net torque? The positive part of the dipole was down here. Positive charges experience the direction of the force in line with the field. So this positive part of the dipole is going to experience a force in that direction right there. This negative portion is going to experience the same force, but in the other direction, like that. Now, those forces are equal and opposite, but they are going to produce a torque on this dipole. So this dipole is going to tend to rotate counterclockwise.